First Spin. Welcome to First Spin, a show where I learn how to use the parallax propeller without having any prior programming experience. Rather than do this on my own, I have enlisted the help of two experts.
Again with you and the expert thing.
Deal with it.
Every week. I'm Whisker, and we also have Mr. Roy Eltham.
Hello.
Hello, Roy.
Hello, Roy.
Do you think maybe this week we should just ignore Addie and get some code done?
Well, the whole point is to teach Addie a thing or two.
Oh, well, yeah, I guess we could do that.
Education.
It is kind of fun, you know. Even I learned stuff listening to this. Roy knows some of the nitty-gritty details that I would have just skipped over when I was learning this stuff.
Right. And I don't like skipping over
No,
things.
Addie is, no. She needs to know every little detail. It's great.
Yep, as much as I can anyway. So last week we finished up on actually our first bit of code, the underscore clock mode and underscore X in frequency.
Yeah. I personally find that little bit of code was one of the most complicated things when trying to learn how to use the propeller.
Yeah.
Because
Why?
I do almost every single project I do requires precise timing because
Yeah.
I do a lot of audio projects.
Sure.
So being able to understand those two lines took ages for me. I didn't have anyone to ask at the time. So the fact that you're going in right from the beginning, knowing how to precisely control the speed at which instructions happens is going to empower you to be able to have so much easier of a time than I did.
Well, I'm glad.
Right.
And actually,
So
go ahead.
I was going to just say that those two lines at the top are actually in what is called the con section, which is for constant, C-O-N for constant.
Okay.
They're at the beginning of your program, typically at the beginning in the first con section, you'll have those two lines.
Okay.
And the prop tool compiler automatically reads those two lines and behind the scenes sets the clock register for you when your program gets loaded up, right?
Okay.
But you can also use the clock set instruction in your code to set those values to whatever you want.
What do you mean?
So the same values that the clock mode and XIN
Frequency?
XIN frequency lines,
Yeah.
you put in those keywords that equal setting up the clock to a certain setting. The clock set instruction allows you to set the register directly with the equivalent settings that you can from those two lines.
I guess is it an internal? So this would be where you set what the internal clock will be?
Right. No, so what we're saying is that the same thing we covered last week where you can set those two lines at the top of your program to determine what the program will run at for whether it uses the internal or external clock and what multiplier to use on the PLL and the clock frequency of the crystal.
Yeah.
You can set those values at runtime in your program. We talked a little bit about that. The way you do that is with the clock set instruction.
And how would you write that out?
Well, you first would go most people don't know this off the top of their head, so you would go to your clock set instruction description in the manual, and it has information about what values to pass in to the clock set instruction and what they equal for setting the clock mode and whether to use the internal or external and what multiplier to use.
Yeah,
so
and I would definitely back Roy up on this where having that manual around, like an actual paper copy of it, makes coding on the thing just so much nicer because you can just page there's a nice table in the center that has a whole bunch of the different operators and such. And it's got sort of index style page numbers to where they live, you know, the big explanations on how all of them work and all of the little tricky details that you can do with each of them. So you may know one of the ways to do something off the top of your head, but there may be 3 other tricky details about it that you didn't know that you should be aware of. Just by looking at the manual, you'll see that they're there. And that makes it easier for me because I don't have to keep the entire programming system in my head all the time. I can just keep most of it in the manual and enough of it in my head to know where to look, right?
Right. So, okay, now you keep saying that it's at runtime. Does that mean it's before everything starts, or is that during?
Well, so like I said, the 2 lines at the top of the program
Right.
are going to set it at the beginning,
Right.
before any of your other code runs.
Right.
But if you use the clkset command in Spin or the clkset instruction in PASM, you can do it in the middle of your program. You can change the setting.
Now, why would you want to do that?
Like I believe I covered that last week. Was an example is if you wanted to put the processor into a low power mode, one of the ways to help it draw less power is to turn the clock to
From
the internal
crystal to the internal.
to the internal slow clock.
Got it.
And that causes it to draw less power because there's less clock frequencies going by, right?
Got
and
it.
so you've got less electricity being pumped through all of everything to do all the instructions.
Got it. Now, when you want to switch it back to the crystal, do you also use this clkset mode?
Right. So if you're going to switch into or out of whatever mode, you would use this instruction to do it.
And clkset, I guess, trumps clock mode
Right.
in the con
trumps.
section.
Yeah, it trumps the setting that's up at the top. It overrides it to the new setting.
Okay, that makes sense. And is it like clock_clkset equals?
No. It's in Spin. You just say clkset, and then there's the open parenthesis, and it has the mode value, comma, and then the frequency, which is that second number that's on the other line. And the mode value, there's a table in the book that tells you what values equal what settings. So you can figure out if you need to use the, what internal clock or external clock, the value is one special value for each of those. And, the PLL settings and all that. So there's a table that you can go look up yourself independently to figure out what all those settings are. But that's the instruction you would use or the command you would use to be able to change it.
I see.
It's similar to the 2 lines at the top, right? You're passing in 2 values. One of them is the mode and one of them is the frequency.
Okay, and then our mode is crystal plus PLL. The clkset mode would be...
It's a binary number of bits on and off that equal the same thing as crystal 1 plus PLL 2.
I see.
And like I said, there's a table you can go look up what all those values are equal to.
Well, that's too bad they didn't call it Buddy, and say, now I want the clkset to go to Buddy. Have him handle it for a while, and then, all right, Buddy, you're done. But okay, I get it.
Okay.
Cool. Very cool. So we actually finished the pin descriptions last week, and we got a little bit into the specifications for the chip itself. So is it okay with you guys if we continue by finishing up that, if we can?
Yeah, whatever questions you have. I mean, that's really the point, right?
Yes. Okay, so the model is P8X32A. So is it the goal of all chip manufacturers to smash together a whole bunch of letters and numbers and say congratulations?
Well, that's part of the reason that Parallax calls the chip the propeller chip, is to make it a more friendly name.
Sure.
But the P8X32A is referring to the 8 cog chips and the 32 I/O pins.
Ah, I see.
Like, for example, what is the actual chip that the Arduino system is burned onto?
It's an
Atmel.
Atmega 328.
So there you go.
And I actually think it has an even longer number than that, but they call it the Atmega 328 as it's shortened.
Yeah, the
the
Atmega
short-
328 is the short version,
It's its nickname. That's
Yeah.
great.
So you know.
Okay, well, at least All right, then I am thankful that there is meaning. So
Yeah.
8 cogs, 32 I/O pins.
Hmm.
Excellent. Okay. Power requirements: 3.3 volts DC, and we got that. And the max current draw must be limited to 300 milliamps. All right, I don't have a problem with that. External clock speed. We did talk about clocks, so DC to 80 megahertz, and the crystal can be 4 to 8 megahertz with the clock PLL running.
Right.
Okay.
But if you have the clock PLL off, then you can use the higher crystals that we talked about last week.
Correct.
With those extra settings.
Got it. And the system clock speed. Now, I had a question. Do you use the system clock with PLL as well?
Well, the system clock is just what clock rate is the chip actually running at. The external clock is what's the external crystal running at.
Okay.
Right?
So when you've got a 5 megahertz crystal attached to it, that's going to be 5 megahertz.
Right.
But the actual speed, if you're running a 16x PLL, is going to be 80.
80.
Right.
And that's
So
what they mean by system clock speed.
Correct.
Okay.
So the
that's,
system clock speed is the overall clock speed after you've applied your clock settings appropriately.
Okay. Okay. And actually, I guess the question would be more appropriate for the next line because it's the internal RC oscillator. Internal, I think it's resistor capacitor. Well, whatever. It's the oscillator, and it says 12 megahertz or 20 kilohertz, and it can range respectively. So it's that like drifting internal clock.
Right. And those are the two other options you can put on those the mode line. Instead of using the crystal, you can use RC fast or RC slow. And RC fast is the 12 megahertz plus or minus a little bit. And the RC slow is the 20 kHz plus or minus a little bit.
And so I think this is where I was going to ask again. So then do you set PLL with this as well?
No. The internal oscillator you can't do the PLL circuit with, only the external clock.
Okay, so it's straight up either 12 megahertz drifty or 20 kilohertz drifty.
Right.
Ah, I see. Okay, got it. All right. Quick question. So one of the main reasons you would want the clock cycles to go slower, would that be like to conserve power?
Right. We discussed that.
Okay. Just clarifying. Double
right,
clarifying.
Yeah. It's so that you can run off of like a battery for a really long time. You can use the RC slow and it will draw very low power compared to running off of a crystal.
Got it. Okay. Main RAM and ROM. So the RAM looks... Oh, okay. So total it's 64 kilobytes, which consists of 32 kilobytes of RAM and 32 kilobytes of ROM. Now, if I remember correctly, ROM is what is like done by the manufacturer. It's hard-coded. It's you can't erase it. That's it.
Right. It's read-only memory, and it's transistors on the chip that are arranged in a certain way to read out specific values that are pre-coded in there.
Okay. And then the RAM is what we write our program to.
Right.
And does that mean we get 32 kilobytes worth of memory?
There's 32 kilobytes of hub memory, the shared memory that we talked about.
Okay.
And as you can see, the very next line talks about cog RAM.
Yep.
And
each
cog, there's 8 of them, has 512 32-bit values, which is equal to 2K of 2 kilobytes.
Okay.
But the reason that they use 512 in this case is because all of your instructions running in the cog are longs. They're 32-bit values. So whenever you have one instruction, it takes up a 32-bit value. So you can really only have up to 512 instructions, but actually minus a few because there's some special registers at the end
of the cog
that are reserved in each cog. Yeah.
Okay. So what's hard coded into the ROM then?
In the case of the propeller, there's a character ROM. It's an image map of all the letters and symbols of a font.
Okay.
There's some sine, cosine tables,
Wow.
and then there's the spin interpreter program, which is the program that is written in PASM that gets loaded up into a cog and runs spin code.
Okay. Okay. So can I ask, if you're writing to the RAM, okay? Does the RAM? Do you have to finish writing the RAM before it can execute, or can you simultaneously write the RAM and have the RAM be execute, or like have the program be executed?
Well, initially, when you first reset the processor and it loads up, it basically reads in either from the serial port, the USB serial connection, or from the EEPROM. It reads in 32K of data and fills up the RAM and does that all before it does anything else. And then it starts running the program at the beginning of that 32K that it loaded in. Once you are up and running, a cog, one of the cogs could be running code that would change the RAM to something else. And then you could do whatever you want. But initially, it just reads in all of the data from either the serial communication or the EEPROM and fills it up before it does anything else.
So then,
keep in mind here, Eddie, that it can use that RAM to store variables,
yeah.
to work on data, and it exists in that RAM as well, if it's an assembly program.
Okay. Yep.
So I know we're mostly going to be talking about first
spin. Yeah.
But if it's an assembly program, theoretically, it could actually change its own bytes of its own program, making it a polymorphic program.
That would be cool.
That can reprogram itself on the fly. That's the sort of stuff
and
I'd
it does
like
that
to get into at
with
some
the
point.
cogs, though.
Yeah, inside the cog memory, yeah.
Yeah, well, see, all of your programs are actually running on the cogs. The cogs are the actual processors. The hub memory is just the shared resource, like we said a couple times before, of the cogs.
I guess what I was thinking was, okay, so you have your cogs, which have 2K of memory, 2 kilobytes of memories that I can work with. Shared has 32. So I was thinking, well, to me, that doesn't sound like much because I'm used to dealing with, gigabytes on my computer.
Sure.
Right? And so I'm thinking, well, maybe my program needs more space than that. So what if I, as I shunted the 2K of information to a cog, that would free up 2K in the shared, and then and then through the serial port, transfer more into the shared hub from my computer. And that way you would have a constantly, I don't know, shifting program, where
you could do that, although it wouldn't work with the prop tool that way. You'd have to write a program for your computer to feed the data. There's actually quite a few options there. There's people that have hooked up external memory to the propeller, some of the I/O pins, and read program data from that external memory and put it into hub memory so they can run from other cogs. And so they do that thing that you're talking about, which is called paging. They page in more of the program into parts of the hub memory to run it. The new C project, the GCC project that Parallax has some people working on, has a mode where it can do that.
Okay.
To run very large programs, because C programs can get really big.
Right.
But you'll find that for the most part with Spin, it's pretty compact. You can get a lot done in 32K because Spin is interpreted bytecode language, which means it's really compact. And so I wouldn't be too worried at this stage that you don't have enough memory.
Okay. Okay, because I know, I've wanted to work with WAV files, music, or not music, but sound
clips. Look at
clips.
it this way. I have done quite a few, what would be considered heavy lifting projects with the platform.
Yeah.
I still haven't run out of memory yet.
Oh.
Right. And Typically for like wave files like you're talking about, you could hook up an external device that holds the wave file, and you could bring it in a little bit at a time into the propeller and play a little bit of it. And there's programs out there on the Object Exchange that will do that from an SD card.
Cool. Okay.
So that's a solved problem.
Gotcha. Okay. So then this 32 kilobytes of ROM, that's something that you can direct your program, your cogs to access?
Right.
With your, okay.
So like there's an Object Exchange program out there that will use the character ROM in there to draw text on the TV.
Cool.
And there's programs that use like the sine table.
For trigonometry math.
Sure.
Right?
Sure. I sense a satellite tracker in my future.
Possibly.
That would be awesome. Okay, so then CogRAM 512, that's 2K of good stuff. And then RAM ROM Organization. You have a long, which is a 32-bit, which you said is an instruction. And is an instruction considered like would clock mode, _clock mode be considered an instruction?
Well, in that case, that underscore clock mode is a constant value, but the clock set instruction is an instruction.
Okay.
So it would be in 32 bits.
Okay.
What this line is telling you, the RAM ROM organization, is that when you're reading the RAM or ROM from a cog, you can access it in 32-bit or 16-bit or 8-bit addressable space.
Okay.
There's different instructions for reading bytes, which are 8 bits, or words, or longs.
Okay.
That's all that line is telling you.
Okay. And is there like an ideal way of organization? Like when you're writing your code or what have you, and like say you're counting your bytes and you're counting your bits, right? Like, is it more ideal to have it in sets of 32? So, go ahead.
Well, the for spin code, you don't actually count the bits per se. You just write spin code as, you put in all the different commands and keywords that execute what you want, and the compiler turns that into a stream of bytes automatically for you.
Okay.
And that the spin interpreter can run and do what you told it to do in the code.
Right.
All that you need to do is like the compiler will count up after it's done that. It'll tell you like how many bytes it used up.
Okay.
When you're doing more advanced programming with the PASM code, all of those are longs. There's no bytes or words for PASM. PASM is always longs.
Oh.
Because the cog always reads a long at a time to execute.
I think she's also was sort of asking about when she's creating variables to store things in, if she creates a byte and then creates a long right after it, she would be wasting 3 bytes of memory.
Right.
So I would be wasting 3 bytes.
Yeah, so what you'd want to do is put the long first and then the byte afterwards.
Okay, so then what if I had... So long is 32, word is 16, byte is 8. So let's say I had 1 long, 1 word, 2 bytes.
Then that would all work out.
So that's fine. But then I would be wasting it if I had a long, a byte, a word, a byte.
Right.
How much does that waste? Like, how much waste is that? I mean,
you would waste a few bytes because they have to be aligned appropriately depending on what they are. So a long has to be long aligned, and a word has to be word aligned. So what that means is that each word starts at every other byte, and each long starts at every 4 bytes, starting at 0. So if you had at the beginning of memory, you had a variable that was a byte, and then the next variable was a long, well, the long has to start at address 4 instead of address 0.
Well, that's a waste.
Because it has to be aligned.
Right.
It works very much like music. You get your whole note, you get your half note, you get your quarter note. There is a quarter note on every single whole note. there is, a
Yeah.
half note on every single whole note.
Okay.
Right.
I get it. Interesting. Okay. But you have to account for that in spin as well. So it's actually
Yeah.
almost easier in PASM because they're all longs anyway.
Yeah, because in PASM you're only dealing with cog memory and the registers in there. Now, when you want to access hub memory from PASM, you are dealing with words and bytes also
Okay.
when you access hub memory.
Okay. Got it. Got it. Okay. I/O pins, 32 CMOS signals with VDD divided by 2, so that 1.65 if VDD is 3.3 volts. Input
Right.
threshold, and that's just high is greater than 1.65 volts, low is less than.
Right.
And then current source sink per I/O 40 milliamps, which we talked about.
Right.
Then current draw at 3.3 volts at 70 degrees Fahrenheit, 500 microamps per MIPS,
And we talked about MIPS last week.
million instructions per second.
She
Right.
can be taught.
Now, current draw, that means it requires 500
Yeah.
microamps.
For each MIP that you are using in your code, it will draw 500 microamps. And notice the formula after that. So if your frequency divided by 4, because each instruction is 4 clocks typically, times the number of active cogs. So if you are using 20 MIPS, then you're going to use 20 times 500 microamps.
Okay.
Right?
Yep.
If you're only using if you have it running at the one cog running at full speed, which is that's where you get the uses low power by switching into the RC slow mode, and you're only going at 20k hertz, right? So this MIPS formula will equal a much smaller number,
Right.
and so you'll take a lot more code to equal 500 microamps.
Got it.
A lot more instructions being executed.
Okay. Okay. Got
And
it.
you can see, we've talked about it before, electrically, what's happening in there is that electrons are being sourced every single clock cycle to facilitate the transistors doing their switching. So the faster you run, the more it's having to use up to do it.
Right. Okay.
Makes sense?
Okay.
Yep.
Yeah.
So every instruction takes 4 clock cycles to do.
Right. There are some the instructions that access hub memory take longer than that, and we'll get into those later. But all the rest of the normal instructions take 4. And again, that's when you're using PASM, and we're going to be using spin initially, so
okay.
it's completely different because spin is a byte code that's interpreted.
Sure. So that takes a little longer.
Yeah.
Now, do you count, like, does it make sense to sit there and optimize and count how many your clock cycles your thing will take up?
Right. When I'm writing PASM drivers for hardware, I definitely do that all the time. I count the instructions to figure out exactly how many, I'm using and how long there is between this one particular instruction that does one thing and another one. It's because it's important for timing when you're talking with hardware, external hardware that requires specific timing.
And again, can I ask, does it matter how complex that particular instruction is?
Like I said, there's basically 2 types. Well, there's 3, but one is the normal instructions, add and move and stuff like that are all internal, and those are all 4 cycles per instruction. Then there's the instructions that access hub memory or do hub instructions, like clkset sets the hub clock register. Those all take at least 7 clocks and as many as 22 clocks.
Okay.
And it's because they have to wait for their turn of accessing the hub. It goes between all 8 cogs, one after another.
Okay.
And so if it happens to be lined up just right, it'll take 7 clocks. But if it's not lined up correctly, it'll take up to 22 clocks total to get completed because it's waiting for the hub.
Gotcha.
And then the third type are the wait instructions, and they wait on a pin changing or the counter getting to a specific value, and they will sit there forever until the situation that you told them to wait for happens.
Sure. That makes sense.
And so they're variable length, right?
That makes sense. That's like a state of quiescence.
Right.
So, okay.
All makes sense to you, Eddie?
Yes.
Excellent. Well, that's all the time we have for this
So
week.
quick.
Yeah. But we will be back next week, so make sure you think up some more questions to ask us then.
No problem. I always have some.
And all you listeners out there, you can get this podcast every week on Tuesday at firstspin.tv.
Yep.
Don't forget to subscribe with the RSS or iTunes, your phone, whatever. It's all good. That's it for us for this week. Thank you for listening, and we'll see you guys later.
Bye.
Bye.
Bye.